December 13th, 2000, Milwaukee, Wisconsin. 6:47 a.m., temperature 8 degrees below zero. Two of three main support girders in the Hone Bridge fracture completely through, 600 feet of roadway hanging by a single beam. But this disaster began 67 years earlier in San Francisco Bay with a decision between two ways of joining steel, the American way and the cheaper way. 1933. Joseph Strauss stands on Crissy Field, staring across the Golden Gate Strait. European engineers have declared his suspension bridge impossible, 4,200 feet across waters 335 feet deep, with 60-mile-per-hour winds and earthquake risks. Modern welding technology promises 40% cost savings and faster construction. Steel companies whisper about electric arc welding replacing primitive four-man rivet gangs. But Strauss proposes something the experts call obsolete. 1.2 million red-hot rivets, each one heated to 1,800 degrees and driven by precision American crews. Four men working as one machine, the heater, the catcher, the bucker, the driver. Through the steam and hammering of construction sites, these rivet gangs were perfecting something European engineers would never understand. When welded steel fails, it fails catastrophically. But when riveted bridges face disaster, something remarkable happens that modern engineering had forgotten entirely. Joseph Strauss stood at the edge of Crissy Field on a fog-shrouded morning in January 1934, watching his crews prepare for the most dangerous construction project in American history. The Golden Gate Strait stretched before him, 4,200 feet of churning water that had claimed more ships than any harbor entrance on the Pacific coast. Behind him, newspapers still carried headlines questioning his sanity. Bridge to nowhere, the San Francisco Chronicle had called it just 3 days earlier. European engineering consultants had submitted their final reports declaring the project impossible, citing wind loads that would exceed any suspension bridge's capacity and seismic forces that would snap conventional joints like matchsticks. But Strauss wasn't building a conventional bridge. As the first steel arrived by barge that morning, he watched Tommy Finnegan's rivet gang begin assembling their equipment with the precision of a surgical team. Each four-man crew carried tools that hadn't changed fundamentally since the Brooklyn Bridge rose 50 years earlier: portable forges, pneumatic hammers, and steel cones for catching white-hot rivets thrown through the air. The technology looked primitive compared to the electric arc welding demonstrations that steel companies had been promoting across the country. Bethlehem Steel's latest promotional materials promised 40% labor savings and twice the construction speed with their new welding systems. Finnegan fired his forge to exactly 1,800 degrees while his crew tested their timing with cold rivets. The heater, the catcher, the bucker, the driver, each man's life would depend on the other's split-second coordination 700 feet above the bay. Strauss had spent months studying rivet gang operations, timing their movements with a stopwatch and calculating the mathematics of their precision. A perfectly driven rivet created a mechanical bond capable of withstanding 40,000 pounds of stress. But more importantly, it created something welding could never achieve: a drilled hole that would stop crack propagation dead in its tracks. The engineering principle was elegant in its simplicity. When stress concentrated at any point in a riveted structure, the load distributed across multiple connection points. If one rivet failed, the surrounding rivets absorbed the additional stress without compromising the entire joint. Each rivet hole acted as a crack arrestor, preventing the catastrophic unzipping failures that plagued continuous structures. European engineers dismissed this redundancy as wasteful, preferring the theoretical efficiency of uninterrupted welds that distributed stress evenly across entire structural members. Harrison Steel arrived at the construction site that afternoon in a black Packard, carrying leather portfolios filled with cost analyses and efficiency projections. As vice president of Bethlehem Steel Corporation, he had watched the Golden Gate project with growing concern. Every rivet driven by Strauss's four-man gangs represented lost profits from welding equipment sales. Steel's company had invested heavily in electric arc welding technology, training programs, and marketing campaigns designed to convince the construction industry that riveting was obsolete. "Mr. Strauss," Steele called out as he approached the construction supervisor's trailer. "I've brought updated cost projections that I think you'll find compelling." He spread blueprints across Strauss's desk, pointing to sections where continuous welds could replace hundreds of individual rivets. "We can reduce your labor costs by 38% and cut 18 months from your construction schedule. These rivet gangs are skilled men, but they're expensive and slow." Strauss studied the welding specifications with the careful attention he gave every technical proposal. The mathematics looked impressive on paper, continuous joints that tested stronger per pound than riveted connections, with clean stress distribution patterns that eliminated the material waste of drilled holes. But Strauss had visited structures where early welding experiments had failed, and the failure patterns troubled him. Welded joints that cracked didn't just fail locally, they created stress concentrations that propagated through entire structural members like lightning through metal. Dr. Wilhelm Hartmann arrived from Berlin the following week, carrying credentials from the German Engineering Association and letters of introduction from European bridge builders. His reputation preceded him, the theoretical architect behind 3 major suspension bridges in Germany and author of definitive papers on continuous joint construction. Hartmann toured the Golden Gate construction site with barely concealed disdain, watching rivet gangs heat, toss, catch, and drive their primitive fasteners while modern welding equipment sat unused in warehouses. "This is not engineering," Hartmann confided to Steele during their evening meeting at the Palace Hotel. "This is industrial archaeology. European bridges use scientific principles, calculated stress distribution, materials efficiency, construction speed. These Americans cling to outdated methods because they fear progress." He pulled out photographs of German bridges featuring seamless welded connections that appeared impossibly elegant compared to the rough, hole-riddled steel rising above San Francisco Bay. But Finnegan's crews were achieving something that impressed even Strauss's conservative engineering estimates. By March 1934, they were installing 8,000 rivets per week while maintaining perfect quality control. Each rivet was inspected by hammer testing. Loose connections rang hollow and had to be drilled out and replaced. The process seemed inefficient, but the results were undeniable. 0 structural failures, 0 crack propagation, 0 catastrophic joint separations that had plagued early welding experiments. The numbers told a story that corporate efficiency experts refused to acknowledge. Riveted connections grew stronger with age as the steel work hardened around the mechanical fasteners. Thermal cycling from temperature changes actually improved joint integrity as the materials settled into optimal stress patterns. Meanwhile, early welded structures showed disturbing tendencies toward brittle fracture as residual stresses from the welding process accumulated over time. As 1934 ended, Strauss faced mounting pressure from steel companies, cost-conscious officials, and European engineering authorities who viewed his riveting specification as an expensive anachronism. But every morning, he watched Finnegan's gangs climb into their steel cages and begin the dangerous dance that would create 600,000 crack-stopping connections per tower. They were building something that wouldn't just carry traffic across the Golden Gate. They were proving that American industrial wisdom could achieve what European efficiency theories promised but never delivered. By January 1935, Tommy Finnegan's rivet gang had perfected a deadly ballet 700 feet above San Francisco Bay. Each morning before dawn, they climbed into steel cages suspended from the growing tower structure, carrying portable forges, pneumatic hammers, and buckets of 1 3/4 diameter steel rivets that would spend the day glowing, white-hot in 40-mile-per-hour winds. Finnegan had earned his nickname, the Heater, during 15 years of bridge construction across the Northeast, but the Golden Gate demanded precision that surpassed anything in his experience. The science of hot riveting required split-second timing and absolute temperature control. Finnegan fired his portable forge to exactly 1,800 degrees Fahrenheit, monitoring the coal's color and adjusting airflow with instruments calibrated to the decimal point. Too cool, and the rivet wouldn't expand properly in the hole. Too hot, and the steel would burn, creating weak spots that could fail under load decades later. At precisely the right moment, he gripped the glowing rivet with long-handled tongs and hurled it through the air to One-Eye Toretti, whose steel catching cone never missed despite wind gusts that could knock a man off the tower. Toretti had lost his left eye to flying steel on the Hellgate Bridge in 1916, but his remaining vision had developed supernatural accuracy. He could judge the trajectory of a thrown rivet in variable wind conditions, positioning his cone to catch the white-hot fastener without letting it cool below optimal driving temperature. The margin for error was measured in seconds. A rivet that cooled below 1600 degrees wouldn't fill the hole completely, creating loose connections that would fail inspection and require drilling out for replacement. Behind Toretti, Mike "the Bucker" O'Malley held a heavy steel backing bar against the rivet's tail, while Hammer Johnson positioned his 90-pound pneumatic driver against the head. The pneumatic system delivered precisely calibrated impacts at 120 pounds per square inch, driving the hot rivet until its head measured exactly 1½ times the shank diameter. Too little driving left loose connections. Too much driving damaged the rivet's internal structure. O'Malley could feel the rivet's expansion through his backing bar, sensing the exact moment when the hot steel filled the hole completely and began forming the final head shape. Each completed rivet created a mechanical bond that defied the theoretical predictions of welding advocates. When Inspector Patrick Murphy tested connections with his ball-peen hammer, properly driven rivets rang with a clear high note that indicated perfect fit. Loose rivets produced a dull sound and had to be cut out with acetylene torches, drilled clean, and replaced, a process that could take an entire day for a single connection. But Finnegan's crew achieved a 97% first-time success rate, installing 8,000 rivets per week while maintaining quality standards that exceeded Strauss's specifications. The mathematics of riveted construction revealed principles that European continuous joint theories couldn't match. Each rivet hole was drilled 3/32 of an inch larger than the rivet shank, creating clearance that allowed thermal expansion without binding. When the hot rivet cooled and contracted, it pulled the connected steel plates together with tremendous clamping force, creating friction that supplemented the mechanical shear strength. The total holding power exceeded 40,000 pounds per rivet, enough to suspend 2 automobiles from a single connection point. But the real genius lay in what happened when things went wrong. Stress concentrations that would propagate catastrophically through continuous welds stopped dead at rivet holes. The drilled opening redistributed load across the surrounding material, preventing the unzipping failures that plagued welded structures. If one rivet failed, neighboring rivets absorbed the additional stress without compromising joint integrity. The redundancy was built into every connection, 600,000 individual fail-safes that made the entire structure virtually indestructible. Dr. Wilhelm Hartmann watched the riveting operations through binoculars from Crissy Field, documenting what he considered primitive American methods for his report to the German Engineering Association. His calculations showed that continuous welded joints distributed stress more efficiently than discrete mechanical fasteners, eliminating the material waste of drilled holes and the labor expense of 4-man crews. German bridge construction had achieved remarkable efficiency with electric arc welding, reducing construction time by 40% while creating seamless structural members that appeared more elegant than hole-riddled American steel. Harrison Steel used Hartmann's observations to pressure construction officials throughout the country. His presentations to engineering societies featured side-by-side photographs of German welded bridges and American riveted structures, highlighting the visual superiority of continuous joints over crude mechanical fasteners. The economic arguments were compelling. Welding required only one skilled operator instead of 4-man gangs, reduced material consumption by eliminating rivet holes, and accelerated construction schedules that saved months of expensive crane rental and labor costs. Yet Finnegan's crews continued achieving results that confounded efficiency calculations. By summer 1935, the South Tower had reached 400 feet without a single structural failure or joint separation. Quality inspectors found that riveted connections actually improved with age as thermal cycling from temperature changes seated the fasteners more securely in their holes. The steel around each rivet work-hardened under repeated loading, creating stronger material properties than original mill specifications predicted. The evidence was accumulating in ways that corporate spreadsheets couldn't capture. Older riveted bridges showed remarkable durability compared to early welding experiments that were beginning to develop troubling crack patterns. The Brooklyn Bridge, built with 19th century riveting technology, carried loads far exceeding its original design specifications after 50 years of service. Meanwhile, welded structures less than 10 years old showed stress concentrations at joint locations that worried forensic engineers. As 1935 ended, Strauss watched his rivet gangs climb toward the 700-foot level with growing confidence in his decision to resist industry pressure. Every rivet they drove created not just a connection, but a crack arrestor that would protect the bridge for generations. The old-fashioned American method was proving something that European efficiency theories couldn't explain. Sometimes the strongest engineering solutions looked primitive to observers who measured only laboratory test results instead of long-term structural performance. The Golden Gate Towers were rising on foundations of proven American industrial wisdom that no corporate cost analysis could calculate or replace. By March 1936, the Golden Gate South Tower pierced the San Francisco sky at 746 feet, its riveted steel frame swaying a calculated 16 feet during earthquake simulation tests, without a single joint showing stress. Each tower now contained exactly 600,000 rivets, everyone installed by crews who had pushed human precision to limits that astonished even Strauss. The bridge's main cables were being spun across the completed towers, 80,000 miles of steel wire that would suspend 4,200 feet of roadway from connections that redistributed stress across millions of individual contact points. Tommy Finnegan stood on the tower's peak that morning, watching fog roll through the Golden Gate while his crew prepared for the final phase of cable anchorage work. The view encompassed the entire San Francisco Bay, but Finnegan's attention focused on the steel beneath his feet. Every rivet his gang had driven created a mechanical bond that grew stronger under the cyclical loading of wind and traffic. The tower's framework absorbed tremendous forces through discrete connection points that allowed controlled movement without catastrophic failure modes. Harrison Steel arrived at the construction site carrying urgent telegrams from Bethlehem Steel's corporate headquarters. The company's investment in electric arc welding technology had reached critical mass, with new training facilities opening across the country and marketing campaigns targeting every major construction project. Steel's quarterly reports showed that welding adoption was accelerating in industrial construction, but prestige projects like the Golden Gate remained stubbornly committed to outdated riveting methods that undermined welding's credibility. "Mr. Strauss," Steele said, spreading updated cost analyses across the project supervisor's desk, "we're looking at a paradigm shift that will transform American construction, the Triborough. Bridge Project in New York is considering all-welded approach for their main spans. The Delaware Memorial Bridge Consortium has requested welding specifications for their entire superstructure. Even conservative engineers are recognizing that continuous joints represent the future of large-scale construction." Steele's presentation included photographs from German bridge projects that showcased the aesthetic superiority of seamless welded connections. The Cologne-Rodenkirchen Bridge featured elegant steel arches without visible fasteners, creating clean lines that made riveted structures appear crude by comparison. Construction time had been reduced by 38%, labor costs cut by 42%, and material efficiency improved through elimination of rivet holes that German engineers calculated as pure waste. Dr. Wilhelm Hartmann had returned to Berlin but continued sending technical reports that influenced American engineering opinions. His analysis of Golden Gate construction methods appeared in prominent engineering journals, contrasting scientific welding principles with primitive mechanical fastening systems. Hartmann's calculations showed that continuous welds created optimal stress distribution patterns, eliminating stress concentrations at discrete connection points while providing superior strength-to-weight ratios. Yet forensic evidence was beginning to contradict theoretical predictions about welded construction superiority. The Quebec Bridge disaster of 1907 had demonstrated catastrophic failure modes in continuous steel structures, but welding advocates dismissed the incident as irrelevant to modern construction methods. More troubling were recent reports from early welded buildings showing crack propagation patterns that didn't occur in riveted structures. Welds that failed locally created stress concentrations that spread through entire structural members like fractures through glass. Strauss reviewed these failure reports with growing concern about industry trends. His engineering education had taught him to value empirical evidence over theoretical elegance, and the evidence clearly favored redundant connection systems over continuous joints. Every earthquake test on the Golden Gate Towers confirmed that riveted structures absorbed seismic energy through controlled movement at connection points, while rigid welded frames transmitted shock loads that could exceed material limits catastrophically. The bridge's opening ceremony on May 27, 1937, drew 200,000 pedestrians who walked across 4 lanes of suspended roadway supported entirely by riveted connections. International engineering delegations toured the structure, documenting construction methods that most considered obsolete. Industry magazines published articles declaring the Golden Gate the last great riveted bridge, emphasizing that future projects would embrace modern welding technology for economic and technical superiority. But even as dignitaries celebrated the bridge's completion, Strauss worried about lessons that might be forgotten. His rivet gangs were already scattering to other projects, their specialized skills no longer in demand as welding training programs graduated hundreds of certified operators. Tommy Finnegan had accepted a position with Boston Bridge Works, one of the few companies still maintaining riveting capabilities for repair work on older structures. The 4-man crews that had perfected American precision construction were becoming industrial anachronisms. Harrison Steel's influence was spreading through corporate boardrooms and engineering societies. His cost-benefit presentations convinced project managers that welding represented inevitable progress, while riveting clung to expensive traditions that modern industry couldn't afford. Steel companies invested heavily in welding equipment manufacturing, creating economic pressures that made continuous joint construction irresistible to budget-conscious authorities. The mathematical arguments seemed compelling on paper. Welded joints tested stronger per pound than riveted connections in laboratory conditions. Construction schedules compressed dramatically when single operators replaced 4-man gangs. Material efficiency improved when engineers eliminated rivet holes that wasted steel in purely theoretical calculations. But laboratory tests couldn't simulate the complex loading patterns, thermal cycling, and stress redistributions that occurred in actual service conditions over decades of operation. As 1937 ended, the Golden Gate stood as proof of what American industrial craftsmanship could achieve when precision overcame efficiency calculations. The bridge carried traffic loads that exceeded original design specifications while demonstrating structural behavior that contradicted European continuous joint theories. Every rivet connection served as a crack arrestor that prevented catastrophic failure propagation, creating redundancy that welded structures could never match. But industry momentum was shifting irreversibly toward welding adoption. Engineering schools taught continuous joint design as scientific progress over primitive mechanical fastening. Corporate pressure favored methods that reduced labor costs regardless of long-term performance implications. The wisdom embedded in American riveting traditions was being dismissed as obsolete craftsmanship by efficiency experts who measured only immediate economic benefits instead of structural reliability over time. The Golden Gate's 600,000 crack-stopping rivets represented the end of an era when American bridges were built to last forever, rather than merely meet minimum specifications. The post-war construction boom of 1945 transformed American bridge building into an assembly line of welded steel and compressed schedules. Harrison Steel's corporate revolution had succeeded beyond his most optimistic projections. Major construction projects from coast to coast now specified continuous welded joints as standard practice, while riveting equipment gathered dust in abandoned warehouses. The economic pressures of wartime production had accelerated welding adoption by demonstrating that single operators could replace 4-man gangs while achieving faster construction schedules that met urgent military demands. Tommy Finnegan returned from Navy shipyard duty to find his profession extinct. The Boston Bridge Works had converted their riveting operations to welding during the war, training former rivet gang members to operate electric arc equipment that required entirely different skills. Finnegan's ability to judge steel temperature by color and coordinate aerial construction sequences had become irrelevant in an industry that valued certified welding operators over craft knowledge accumulated through decades of dangerous work. He accepted a position at Bethlehem Steel's mill operations, where his understanding of steel behavior helped troubleshoot production problems, but never again involved the precision teamwork that had built America's greatest bridges. The mathematics of the new construction philosophy seemed irrefutable to corporate executives and engineering graduates trained in welding techniques. Continuous joints distributed stress evenly across entire structural members, eliminating the stress concentrations that theoretically occurred around rivet holes. Material efficiency improved dramatically when engineers no longer wasted steel on drilling holes that reduced cross-sectional area. Labor costs plummeted when construction crews needed only one skilled operator per joint instead of four-man gangs whose coordination required years of training to perfect. Dr. Wilhelm Hartmann's influence had spread through American engineering education, where professors taught continuous joint design as scientific advancement over primitive mechanical fastening methods. University curricula emphasized strength-to-weight calculations that favored welded connections in laboratory testing conditions. Students learned to calculate optimal stress distribution patterns for seamless joints while dismissing riveted construction as historical curiosity that modern engineering had surpassed through theoretical understanding and technological progress. The Mackinac Bridge project in Michigan became welding technology's showcase during the early 1950s. Engineers specified continuous welded joints throughout the 5-mile suspension span, eliminating thousands of rivet holes that would have weakened the structure, according to calculations that measured only material cross-sections instead of stress redistribution patterns. Construction proceeded 40% faster than comparable riveted projects, with labor costs reduced by margins that impressed budget committees and corporate stakeholders throughout the construction industry. But troubling evidence was accumulating in structures that had embraced welded construction during the previous decade. The Silver Bridge over the Ohio River showed crack patterns that didn't occur in riveted spans of similar age and loading. Welded joints that developed flaws created stress concentrations that propagated through entire structural members, unlike riveted connections where cracks stopped at drilled holes that redistributed loads across surrounding material. Forensic engineers noted these anomalies but attributed them to early welding techniques that had been improved through technological advancement. Harrison Steel's corporate success had created industrial momentum that made welding adoption virtually inevitable for major construction projects. Bethlehem Steel's training programs graduated hundreds of certified welding operators annually, while rivet gang expertise disappeared through retirement and career changes. Construction companies invested in electric arc equipment that promised versatility across multiple project types, unlike specialized riveting tools that served only traditional bridge construction methods. The seductive logic of continuous joints convinced engineers that seamless construction represented progress over redundant fastening systems. Welded structures appeared more elegant in architectural photographs without the visual clutter of mechanical fasteners that made riveted bridges look crude to modern observers. Corporate marketing emphasized clean lines and material efficiency while downplaying performance characteristics that couldn't be measured in immediate cost savings or construction schedules. Milwaukee's Harbor Bridge project began construction in 1968, featuring state-of-the-art welded steel plate girders that embodied everything modern engineering had learned about continuous joint design. The bridge's 3 main spans utilized seamless construction throughout, eliminating mechanical fasteners that earlier generations of engineers had considered necessary for structural integrity. Project engineers congratulated themselves on efficiency achievements that reduced construction time by 18 months, while cutting material costs through elimination of rivet holes and associated labor expenses. The engineering calculation supported every design decision with mathematical precision that impressed review committees and federal oversight agencies. Continuous welds distributed stress optimally across structural members, creating strength-to-weight ratios that exceeded riveted construction by measurable margins. Computer modeling predicted service life performance that matched or surpassed older bridges while requiring less maintenance due to elimination of mechanical joints that could loosen over time. Yet the Golden Gate continued operating with remarkable reliability after 30 years of service, its 600,000 rivets showing no signs of the deterioration that welding advocates had predicted for mechanical fastening systems. Traffic loads had increased far beyond original design specifications, but the bridge's riveted connections simply redistributed stress across additional contact points without compromising structural integrity. Thermal cycling from daily temperature changes actually improved joint performance as materials settled into optimal stress patterns. By 1960, America had built its last major riveted bridge. The craft knowledge that Tommy Finnegan's generation had perfected through decades of dangerous precision work vanished from construction sites, replaced by welding techniques that required different skills and produced fundamentally different structural behavior. The four-man crews that had understood how discrete connections created fail-safe redundancy were scattered across other industries, their expertise in stress redistribution and crack propagation forgotten by efficiency experts who measured only immediate economic benefits. The transition represented more than technological change. It marked the abandonment of engineering wisdom that had prioritized long-term reliability over short-term efficiency. American bridges had once been built to last centuries, their riveted connections growing stronger with age while providing multiple failure safeguards that prevented catastrophic collapse modes. The new welded structures achieved impressive strength-to-weight ratios in laboratory testing, but created continuous stress paths that would prove vulnerable to failure propagation in ways that efficiency calculations had never considered. The corporate revolution was complete, but the full consequences would not reveal themselves for decades. Dr. Sarah Chen arrived at the Hoan Bridge disaster site on December 14, 2000, carrying forensic equipment that would reveal the catastrophic vindication of engineering principles abandoned 60 years earlier. The temperature had dropped to 8 degrees below zero overnight, creating the brittle conditions that transformed welded steel into a material as fragile as glass. Two of the bridge's three main welded plate girders had fractured completely through their depth, leaving 600 feet of roadway suspended by a single structural member that groaned audibly in the winter wind. Chen's grandfather had worked with Tommy Finnegan's rivet gangs during the Golden Gate construction, and his stories about four-man crews who understood crack propagation had influenced her decision to specialize in structural forensics. As she examined the fractured girders through her magnifying equipment, she could see exactly what the old riveters had predicted: continuous welded joints that failed catastrophically instead of redistributing stress across multiple connection points. The failure had propagated through 200 feet of structural steel in seconds, creating the unzipping effect that riveted construction was specifically designed to prevent. The Federal Highway Administration's investigation revealed metallurgical evidence that contradicted 30 years of welding advocacy. Stress concentrations at the welded joints had created triaxial constraint, a brittleness condition that accumulated over decades of thermal cycling and traffic loading. When the critical fracture initiated during the December cold snap, it propagated through the continuous weld-like lightning through a conductor, finding no discrete connection points where crack energy could dissipate safely. Chen's microscopic analysis of the fracture surfaces showed classic signs of brittle failure that occurred when welded structures reached their fatigue limits. The continuous joints that had tested stronger than riveted connections in laboratory conditions proved vulnerable to failure modes that didn't exist in redundant fastening systems. Each weld created a potential crack initiation site with no mechanism for containing propagation once critical stress levels were exceeded during extreme weather conditions. Meanwhile, 63-year-old Golden Gate Bridge rivets continued performing exactly as Strauss's engineering had predicted. Chen's inspection team found that the bridge's mechanical connections had actually grown stronger with age, as thermal cycling seated the fasteners more securely in their holes while work hardening the surrounding steel. Traffic loads that far exceeded original design specifications simply redistributed across additional rivet contact points without creating the stress concentrations that plagued continuous welded structures. The mathematical proof was undeniable when Chen compared failure statistics across bridge populations. Riveted structures built before 1940 showed remarkable longevity, with major failures occurring only when catastrophic external forces exceeded all reasonable design margins. Welded bridges constructed after 1950 demonstrated increasing failure rates as they aged, with crack propagation patterns that created maintenance nightmares and occasional catastrophic collapses like the Hoan Bridge disaster. Harrison Steel's corporate descendants at Bethlehem Steel faced liability questions that their efficiency calculations had never anticipated. The welding revolution that had promised 40% cost savings was generating lawsuit settlements and emergency reconstruction costs that dwarfed any labor savings achieved during original construction. Insurance companies began investigating whether welded bridge design represented an acceptable risk compared to proven riveted construction methods that had demonstrated century-long reliability. The engineering community's response revealed how completely the profession had forgotten the principles that guided earlier generations of bridge builders. Modern structural engineers had been trained exclusively in continuous joint analysis, with no education in discrete fastening systems or crack arrestor design. University curricula that had dismissed riveting as obsolete craftsmanship now scrambled to understand why mechanical connections provided superior long-term performance despite appearing primitive to theoretical analysis. Chen's final report documented the fundamental flaw in welding advocacy that had convinced an entire industry to abandon superior construction methods. Laboratory testing of individual joints had measured strength parameters that were irrelevant to long-term structural performance under complex loading conditions. Welded connections that showed impressive strength-to-weight ratios in controlled conditions created continuous stress paths that proved vulnerable to catastrophic failure, propagation in actual service environments. The economic implications were staggering when calculated across America's aging bridge infrastructure. Hundreds of welded structures built between 1950 and 1980 were approaching the fatigue lives where brittle fracture became increasingly probable. Emergency inspection programs revealed crack patterns in welded joints throughout the interstate highway system, creating maintenance costs that exceeded the original construction savings that had justified continuous joint adoption. Tommy Finnegan had died in 1987, never living to see the vindication of riveting principles he had helped perfect during the Golden Gate construction. His obituary in the Boston Globe mentioned his bridge work but focused on his later career in steel mill operations, with no recognition that his craft knowledge represented engineering wisdom that the industry had foolishly abandoned. The four-man rivet gangs that had built America's most durable bridges were remembered only in historical photographs that showed primitive-looking construction methods. But the Hoan Bridge failure forced a fundamental reassessment of structural engineering priorities that had favored efficiency over reliability for 50 years. Chen's forensic evidence proved that riveted construction's redundancy wasn't wasteful. It was the essential characteristic that prevented single-point failures from becoming catastrophic collapses. Each rivet hole that welding advocates had dismissed as material waste actually served as a crack arrestor that could save entire structures from destruction. The lesson was written in twisted steel and emergency reconstruction contracts that cost $16 million to repair what riveted construction would have prevented entirely. Modern engineers began studying historical bridge designs with new appreciation for the wisdom embedded in discrete fastening systems. The Golden Gate's 1.2 million rivets represented more than mechanical connections. They embodied American industrial knowledge that understood how structures actually behave under real-world conditions rather than theoretical laboratory predictions. As Chen completed her investigation, she realized that the Hoan Bridge disaster vindicated not just riveted construction, but the entire philosophy of redundant engineering that prioritized long-term reliability over short-term efficiency. The bridge that Tommy Finnegan's crews had built with seemingly primitive methods had proven superior to every technological advancement that followed, not despite their mechanical simplicity, but because of the fail-safe principles that continuous welding could never replicate. American craftsmanship had built bridges that grew stronger with age, while modern efficiency had created structures that grew more dangerous as they aged.